In this question, we're asked to predict the hydronium ion concentration and pH for a half a mole per liter solution of hydrocyanic acid. So hydrocyanic acid is HCnAQ. If we take a look in our data book on the acid base table, hydrocyanic acid's Ka is equal to 6.2 times 10 to the negative 10. So we can set this up in two different ways. I'm going to show you both the long way first, and then I'm going to show you a shortcut. So to show all of our work when doing this problem, what we'll want to do is we'll want to set up an ice table. So we are going to have hydrocyanic acid reacting with water. Because this is a solution, it will be an equilibrium that creates HCN minus and hydronium ions. We're going to split this ice table up like any other ice table. Forgive my lines. And we're actually going to blot out the water. The reason we're doing this is that water is liquid. Because it's liquid, it doesn't factor in to the Ka formula at all. So our initial concentration, our change, and our equilibrium are what we need. Initially, the concentration of the hydrocyanic acid is half a mole per liter. Because nothing else is explicitly listed, each of these will be 0 moles per liter. We know the hydrocyanic acid is the only thing present, so it has to go down. It will go down by minus x. The others will increase by x. The final concentrations of our two products will each be x. Now, we have to check for our hydrocyanic acid if it passes the rules of 1,000. Is half a liter, or is 1/2 more than 1,000 times greater than 6.2 times 10 to the negative 10? If we do that calculation, we will find that it absolutely is. It is much, much bigger than 1,000. In fact, it is about 8.9 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is much, much larger than 1,000. This means passes the rule of 1,000. Okay, so that's good for us then, because that means that we can just use half a mole per liter as our final concentration as well. Remember, the concentration of HCN is changing, but it's changing so little compared to what it starts at that statistically they're basically the same. For the HCN and the H3O plus, however, that is a significant change because they started at 0. We now know that Ka is going to be equal to the hydronium ion concentration times the Cn minus concentration over the concentration of HCN. Important thing to remember, it's always the equilibrium concentrations we're dealing with here. It's not a big deal in a Ka calculation because oftentimes those do pass the rule of 1,000, but you do need to make sure you're using the equilibrium concentrations. Okay, so 6.2 times 10 to the negative 10 is going to be equal to, well, both of those are x, so we can turn it into x squared and that's going to be over 0.5 mole per liter. Okay. Next thing we're going to do, we're going to bring the 0.5 mole per liter over. That means we're going to have 3.1 times 10 to the negative 10 is equal to x squared. And in order to find x, we're going to take the square root of that. And that is going to be equal to 1 second. That is going to be equal to 1.8 times 1, 2, 3, 4, 5. 10 to the negative 5 moles per liter. Now that gives us the concentration of our hydronium ions. Also gives us the concentration of our conjugate base. We also want to find pH though. However, as we know, calculating pH is going to be equal to the negative log of the hydronium ion concentration. So the negative log of 1.8 times 10 to negative 5 . And that is going to give us a pH of 4.75. So our hydronium ion concentration is 1.8 times 10 to the negative 5, and our pH is equal to 4.75. Those are our two answers.